That is Kei Yoshimura from the University of Tokyo, talking about the predictability of the floods caused by Typhoon Hagibis in 2019 using today's Earth. Kei, we are looking forward to your presentation. I mean, if you would like to try and steal the screen to one.
Juan, can you?
Yes, I did. Okay.
Perfect.
Okay. Hi, everyone. Good evening. Actually, it is now 12:30 in midnight in Japan, so it's kind of harsh timing. But my name is Kei Yoshimura from Japan University of Tokyo, and I'd like to present on the predictability of the floods caused by Typhoon Hagibis 2019 using today's Earth, which is our global flood forecasting system. And then there are a bunch number of names here. So these are our collaborators, and also this work is collaboratively done by University of Tokyo and JAXA. So starting from, I would like to start with some flood events serially occurred over Japan. So it's starting from 2015 events. So I'm going to start the video, but it has some sounds, so please be minded. So heavy precipitation caused by two typhoons, but actually it's not the directly caused by the typhoon, but indirect. But as a result, whole city, Joso city was inundated, and then 10,000 citizens or 11,000 houses were inundated. So actually, it struck me. It was a very shocked moment for myself because it's actually quite close to my residence, and so I was I didn't realize that it also happens to like urban area like near Tokyo. So actually, it triggered our motivation towards the flood forecasting. So three years later, 2018, there was an even worse floods hits occurred in west part of Japan. It is called West Japan heavy rain, and then it was caused by Bayou front, so rain band. But it was 24 accumulated rainfall was all very many record-breaking rainfall was recorded. And then actually it killed more than 200 people. And then the left bottom part, it's a hydrograph at one river called Takahashi River. It is only 48 hours, 2 days in the horizontal axis. And so the hydrograph here, blue line, is very rapid. It's so typical flash flood. But even because of this very rapid change of the water level, so that 50 people could not escape from this basin, then actually more striking is 80% of this casualty was elderly people who couldn't escape even to the rooftop of the residence. So it reminded us the necessity of the longer lead time of the flood forecast. So actually, and then last year, Typhoon Hagibis hit Japan in October, and then it actually caused serious damage over 70 river systems, and then killed more than 100 people. And it's one of the most devastating damage in the Nagano prefecture. And then actually what it was unique here was actually this was ECMWF's typhoon prediction, but the ensemble spread was very small. So the predictability of this event meteorologically was quite high. And then actually we created something called Today's Earth. Please Google Today's Earth, or please click this link if possible, but it's a near real-time land surface simulation system. And then globally 1/4 degree, and then actually it has a regional version over Japan is 160 degree, which is corresponding to the 1 kilometer. So with exactly the same modeling system. And then uniqueness is forced by multiple satellite-based atmospheric variables, including GS-map precipitation or modest radiation. And then it is downloadable up to 1958. So then forecast version is going to be tested, which I'm going to introduce from now. So this is a graphical user interface of the system. And then similarly, it's similar to the GLOFAS or MAGIS system. It has like globally, I mean, zoom in and zoom out system, and then many variables, not only discharge quantity, geophysical quantities, but also return period of major variables as well. So that, and then, as I said, it has a regional version, today TE Japan. And so the system can be ported to any other of the regions. So actually, we are planning to extend it to the other, for example, Indonesia, I mean the Southeast Asia or Africa and so on. This is the data flow, but because of the time limitation, I will skip it. But it has not only physical quantities, but also it has a return period, how rare the values are as well. And then this is a structure of prediction system using today's Earth. So as I said, today's Earth system is until near real time, but as you can use it by using forecasted atmospheric variables, we can apply towards the future. So this is a schematic diagram, and then some video is also showing, sorry, in partly Japanese. We developed a reliable flood prediction system overall Japan, aiming to provide those information well before hazard. So, I mean, it is relatively shorter, I mean, 1 to 2 days, but actually for Japan, I mean, it fits because of short, smaller basin size over, I mean, in total. And then before moving on to the case studies, but I would like to introduce general performance of the system. So we handcasted for 11 years by using that system. And then every 3 hours, we forecasted 33 hours. So every 3 hours, we have 11 sets of forecasting time series. So, and then we assess the accuracy in each lead time. So how the performance is degrading as the lead time longer lead time. And then we use PSS, Pierce Skill Score, to express the performance, which consists of the hit rate minus false alarm rate. And using 850 water level measuring stations over Japan. As I said, it is 11-year handcasted experiments. And then, so horizontal axis is forecasting lead time, and then the vertical axis is a skill score. And then zero reference is when we use, I mean, it's a zero analysis. So using observed atmospheric forcing, and then try to simulate the discharge. So it's a kind of a maximum scale of our system, and it degrades over time. And the reference value is how it interprets the PSS is positive value have a predictability, and then 0.25 it means good predictability. So forecast 33 hours before, it shows having positive PSS at more than 90% out of 850 stations. And then 12 hours before, 0.25, so it means good predictability. So of course, we are not satisfied with this performance, and then there is lots of room to be improved. However, by showing such kind of performance or the evaluation, then user can choose, depends on the purpose, how those kind of information can be utilized for their purpose. So let's move on to the 2015 case and the 2018-2019 case. So 2015, it was actually simulated after the event. So Ensemble Forecast was tested, and then the top one is a precipitation. So there is an ensemble spread from this particular initial condition. And then depending on this precipitation, the discharge is simulated. And then there is a large variance of the ensemble member. However, what it is showing here is we can quantify how dangerous the situations are. So we set the thresholds, and if this is regarded as evacuation level, but by showing the bottom right figure, 39 hours before, 36 ensemble member out of 50 shows more than the flooded or alert, but that rate increases over time. So 15 hours before the actual disaster, almost 100% of the members are showing the sign of floods. So actually, it's successfully forecasted even in the middle size basin, only exceeding 1,000 square kilometers. So it is regarded as a weakness of a global system, but actually it can be applied for such a scale as well. And then this framework is globally applicable. So 2018, actually we draw a similar GLOFAS type table, and then showing red is alert. But compared to the real situation occurred, only 3 hours before, actually there was a alert from the government, but it can be extended towards more than 24 hours, possibly. So it may, this is an example in 2018. And then moving on to just last year. Actually, this figure, this illustration was used when the actual disaster was happening. So exactly the same figure is shown here. So as typhoon approaches, the river discharge amount is increased, turns into green, yellow, or orange, like blood vessels. But that level of water discharge, river discharge is, we cannot convert it to the danger level directly, because there are big rivers or small rivers. So we also simulate inundated area by using the Kei flood model. So Kei flood is able to simulate inundated fraction. So inundated fraction is actually a more fair indicator of the flood. So from totally violet blue color in the beginning, but it suddenly turns into yellow or red in the many places. So it indicated the danger of the danger for those areas, which was predicted day before what is happening. And then it turned out, and actually I was so worried at that time, but actually it happened as somehow simulated or predicted. So according to the authority, there were 142 levee broken sites. And out of that, TE Japan successfully gave alerts, which is defined as once in 200-year water level at 129 sites. So the recall is more than 90%. And then the good point is there is plenty of lead time, more than 30 hours. However, there is what it shows in the figure is white pins are showing a false alarm. So false alarm rate was, somehow 90%, and it varies in time, but about 70 to 80%. So yeah, that's actually a shortcoming. However, we are not so worried about such a large number of false alarm because this is a levee break. And then levee break is when levee break occurred, we actually the safety level of the different place is getting safer. So it means that, and then our system is showing alerts along the river. So actually it isn't so, how can I say, wrong to show pins over the along the rivers here. Well, actually, those information cannot be provided to the citizens directly in Japan, actually. So there, because of the law. So only those information is provided to the municipals right now. And then there are many municipals as a collaborative research right now. So we are trying to find a way to utilize those predicted information with the municipal officers. And then actually there was a flood occurred this year as well. And then there were two very different floods. One is caused in July because of the biofront over Kyushu Island. And then other is Typhoon Taishan in September. And actually Typhoon Taishan was anticipated, July, there was a flood in July, so that Typhoon Taishan was actually very much worried about flood, bigger damage was anticipated as Taishan approached. However, as a result, it did not cause too serious damage. And then our system also didn't show as much as July event. So it proved that somehow our correction system is quite right. And then future direction, as a future direction, I would like to introduce newest work done by Mr. Oki. It's a fusion with a satellite observation, especially synthetic aperture radar, SAR. And then today's Earth is shown in the left-hand side, and then SAR is shown here, right-hand side. And then using TE prediction as a prior of the Bayesian estimates of the inundation area, so that actually it helped to improve the inundated area detection. So in terms of the precision and also computational efficiency. So we quickly implemented this scheme into the operation system, so that nowadays we actually in July event, we could use this system to estimate the inundation for the Kyushu Islands floods, promptly announced in case of right after the image was taken. And then actually I concentrated on the Japanese system. So this is an example for the global, one of the global example. And then actually, unfortunately, in Vietnam, there was a series of typhoons, tropical cyclones hits in a row. And then our TE global, even though it is a lower resolution, 1/4 degree, the return period of the discharge is showing the animation here in the daily scales. And then it shows a pretty high value depending on the day, and then it actually it helps to show the alerts. I mean, show the danger level for those areas. So this is the summary, and then because of the time limitation, I wouldn't read it. So thank you very much.